Last time, I built a wire EDM with my old 3D printer, and I got a lot of requests to explain how to do it. So I brought a new printer to show you the process. This machine can basically cut any metal. For example, this piece of aluminum was cut with a great precision. I can also cut copper, so this is an heat pipe from a PC, and even tungsten carbide. For the electronics, I started with this prototype. The spark is controlled by a Raspberry Pi, and we have a MOSFET driver that controls a powerful MOSFET. This MOSFET is mounted in parallel with a capacitor. Specifically, it's a film capacitor, which is very efficient at high frequency. I wanted something cleaner, so I designed a PCB, which works the same way. We still have the capacitor, the MOSFET driver, and the MOSFET, but this version is able to measure the voltage across the electrode. I got some issue with the current measurement, so I designed a second version and uploaded it to GLC-PCB, which is the sponsor of this video. GLC-PCB is an online manufacturer where you can just upload your Gerber file and get an instant quote. They offer a large variety of options like aluminum or flexible board and up to 6 layers when signal processing is important. The process is very easy, which makes it a powerful tool for a maker. I received my board just a week later, and it's actually the first time I ordered a PCB, and the ability to get exactly what I designed for such a low price is very impressive. They supported me on this project, so please check the link in the description to get a $30 coupon on a 6-layer board. Okay, let's solder it. So, this is the final board. The current comes from here. We use a standard switch mode power supply. This one can provide 80 volt at 5 amps. Then we need a high power resistor to limit the current in case of short circuit. So we use the heat cartridge from the hot end. So the current goes through a fuse. Then we have the two capacitors to store the energy. And we use a freewheel diode to dissipate the energy from the arc to protect the MOSFET. The powerful MOSFET is just here. The MOSFET is driven by this chip, which needs 12 volts to function. So we use the power from the printer, which goes to this Ethernet cable. We also need a buck converter to transform the 24 volt to 12 volts. To measure the voltage across the electrode and across the resistor, so we have two dividers that are adjustable with two potentiometers. The current is just the difference in voltage divided by the resistance of the heat cartridge. On the other side, we just have a I2C screen, some potentiometer and some switches, and everything is connected with these GST connectors. This machine is switching a lot of current at high frequency, so using an aluminum box to shield the electronic noise is required to avoid damaging any electronic device. We have a few modifications to do on Marlin. We will change the configuration and the configuration advanced file. Everything is in my GitHub in the description. But for now, we just need to go to the pin file, which is here. And we can see that we have 5 UART pins. So we have 1 free RX, and the associated pin is the TX, which is connected to the heater bed pin. Then we can take a look at the pinout of the chip, and we can find the two corresponding pins, so PI2 and PI3, and their location is given here. As you can see, I have soldered two wires to this chip. They are connected to the BL Touch connector that goes directly to the Ethernet connector. We also have the power on this cable for the PCB. The UART communication is used to adapt the speed to the current and voltage. Here you can see that the speed is reduced when the average current is above 1 amps. We are done with the electronics. Now I have to solve the backlash issue. In the first version I use this reducer. It has a lot of backlash, so I measured it with a comparator by going back and forth, and the result is about 400 microns. To solve this issue, I designed this belt reducer. that is way more precise. When the belts are tensioned properly, it can have a backlash of around 50 micron. I like the design though, so I might use it for another application. In the end, I went for the obvious solution, which is a lead screw with an anti-backlash nut, and it can go down to 10 micron of backlash. This is the machine with the new modification. I used the belt to move the motor to the back, and I also removed the Z-axis, which is useless for wire EDM. This is the first piece I made with the new modification, and you can see that the features are very well defined because of the low backlash, and the bearing is fitting perfectly. I haven't figured out a way to cut the wire automatically, so I have to make a continuous path with all the features. Now that everything is working, we can start the modification, and the first step is to dismantle the new under free. Just keep in mind to not throw anything away, because we will use all the parts. We'll start with the x-axis. I've added a linear rail, and I also cutted this aluminum piece to allow the belt to pass from one pulley to the other. The measurement is fully printed, and it's adjustable so we can tension the belt properly. Then we have a lead screw with a 2mm pitch, locked in place by this 3D printed nut, and we use an anti-backlash nut from Open Builds. And the lead screw is supported by two bearings that come from the original belt tensioning system. For the y-axis, I just use this 3D printed piece to mount the motor. The carriage is wide enough so we don't need to add a linear rail, and I just need to drill 2 holes to mount the anti-backlash nut. This underfree has been modified with a third-party board, which already has a TFT port with UART communication, so I just have to plug it in. Overall, I'm very happy with the machine. It took me a few hours to do the modification I showed you, and it cost about 100 euros, 50 for the electronics and 50 for the mechanical parts. Next time, I will focus on the wire feeding mechanism as well as the water filtration system. You can find everything you need on my GitHub in the description, and I also created a Discord server. I hope you enjoyed the video. If so, please don't forget to like and subscribe, and thank you for watching.